Thank you very much for this introduction. So I should very similarly tell you that this work is mainly done by my PhD student, Shu Li, that I was just very happy to just help him through developing this work. So when I look at the slides that Shu prepared, I thought that possibly we needed much more background on plug and play and this sort of thing. But luckily, I'm just presenting after two great preliminary talks. So I'm happy that we don't have this sort of issue. So just want to say that possibly in this talk we will see a little bit, we will see plug and play, definitely, but we will also see how we can just get away from supervised learning, and we will see why we call this self-supervised learning. And we just started with some kind of formulating the problem in the form of optimization, and then gradually I will show you that how we can just use replace different components which are very much expensive for the application of hyperspectral inpainting, and we can just replace with some deep neural network, but it has been used in a different way. Okay, so after giving some background, I will just talk about the proposed algorithm. I will show you some numerical results, and I will just tell you what we think would be good direction for the future work. Okay, very similar to many mentioned problems that we had a chance to look at today. We are dealing with a sort of data, the dimensionality is very high. So hyperspectral data is a sort of data that we see it in Earth observation and in defense when we are not dealing with RGB simple images. So we simply have more spectral bands. So it looks, by definition, it looks very easy to just collect this data and handle. But if you assume that the simple image is 100 by 100, so we have 10,000 pixels, then if we have 100 different spectral bands, it would be multiplied with 100, and the problem size become in a way that we may not just be able to handle it very efficiently using deep neural network, particularly considering the fact that we need to just have enough training data to just come up with some reliable models. So we want to deal with this, let's say, big size data problem. And specifically the problem that we have focused here is called hyperspectral inpainting. What it means. So we have array of, let's say, photodiodes that to just enable having color, 3 different colors, we just put some micro filters, let's say red, blue, green, most of the time 2 greens, on a grid of 2 by 2, and then we just record different filtered lights at each, let's say, a small area of 2 by 2. But if you want to scale it up to 100 and sometimes 1,000 different spectra, that's simply not the technology that we have it. The technology that we have most of the time, I mean, unless you are just talking about very expensive, very power hungry, and specifically designed for some security applications, what you have is push broom technology, which means that what we have is the array, but at each time we are looking at one, let's say, line of the image, and we have some sort of, let's assume a prism that we just record of one line here, not only the amplitude at one particular band, we just have all the bands. But the catch is that we need to just, like a push broom, we need to just over the area and collect, and sometimes we need to average over them to just have reliable measurements. But the point is that in many times, because of, I mean, if you have airborne or spaceborne, there are some cases that you are missing some of the lines due to some imperfections. And also, if it's a spaceborne and you have some dead pixels, that pixel is dead forever. You don't usually go and fix the satellite. So that band or that, let's say, pixel would be dead forever. So you need to just have a mechanism to just kind of best estimate the band. So this problem can just be then formulated as what we measure of the, let's say, okay, what you measure is, I mean, what you want to measure is X, but you have a matrix M, which kind of subselects the data, you add noise, and what you measure is at the end Y. Okay. So it is different to compressed sensing, because in compressed sensing, you have this chance to design M such a way to satisfy some properties. Is not as bad as super resolution. So it's something between compressed sensing and super resolution. So this has been done massively for the image. So for image in painting, when you have some holes in the RGB image or a black and white image. So there are some solutions. But what we have found is that the scalability of those solutions to hyperspectral domain is very much limited. Okay. So, I mean, we didn't want to just specifically talk about the shortage of these two algorithms. We want to just give some examples that you have some issues in terms of, you cannot just scale up, and sometimes you need to just know, you need to just have some conditions satisfied. This means that you need to just have some measurements at each pixel in that band. Otherwise, this solution just fails because they are just inverting a matrix that it becomes singular, and you cannot just simply deal with these cases. So recently, like many other applications, deep learning has been applied to this particular problem as well. And they produce state-of-the-art, not surprising. But the point is that we are dealing with a very large size problem. And this means that we need to just deal with the even bigger training data sets to be able to reliably train. Can we just get away from, this training step? Okay. So one step back, I just want to say, what is the conventional state-of-the-art conventional techniques, not deep learning based? So there are two models that we have in hyperspectral data. One of them is that this data cube usually is just very close to low rank. Okay, and that's definitely related to the redundancy of this data. Not all the spectral bands are independent. So you have some dependency between the spectral bands. And also it demonstrates some sparsity in some dictionaries. So this has been massively exploited after the introduction of compressed sensing, just saying, oh yeah, this data is sparse. And for phi, there are techniques to just find phi as, using some of the exemplar n members, means that representative spectral, or just doing dictionary learning, which is very much well understood. So now we have two constraints, and what we do in practice is that we have an operator which just select a patch of image, and we assume that that patch is sparse. And because we are just putting it in ADMM framework, so we have some auxiliary variable u, and which supposed to be at the end equal to x as a constraint that we introduce. So we can just split the update based on u and x and alpha. Okay, so the conventional solution based on this model, which shows really good results before the, let's say, popularity of the deep neural network, is that you just go and update based on alpha. You just update alpha to just find alpha k plus 1. Then you update based on u. Then you update based on x. And then, you just try to just make, you apply some constraint that x and u to push together to just become equal. Okay, what happens is that if you are just having a sparsity constraint here, so you just have a soft thresholding, which you may just be familiar if you have seen the standard work in compressed sensing. And also here, what we need to do when we have a low rank constraint is just singular value thresholding, which is very much calculating singular value and do soft thresholding of the single values. Okay. So we can do this, but it is very expensive. Okay. And the performance is good, but not as good as deep learning based solutions. So plug and play can just help us. We can just very much, we had a very good discussion on how we need to treat the denoiser, and just put a denoiser on I minus gradient of f. F is just this L2 penalty. And the we found it very interesting that we can replace the single value thresholding operator with something called deep image prior. Okay, so what is deep image prior? Deep image prior is again a solution, or is an approach that initially found very controversial. Is that when we have some deep neural network, including convolutional neural network, even when the network is not trained and you start training based on limited data, first you find some structure of the data, and then you start overfitting because you don't have enough data. So the trick is that to earlier stop the training and just get away. This means that this deep neural network doesn't need to be trained before just using it. And it acts as a regularizer for some inverse problems. So it generated lots of interesting results in image, let's say, in image in painting, by just using some, let's say, customized convolutional neural network for some neural network that has some, good inductive bias. Means that they are not good to just represent noise. Okay, so it's more or less suitable for presenting images. Okay, so how the steps for the algorithm. So we can just select the dictionary, or we can just pre-train it based on available data set. This is not a difficult task. It has been done, and some dictionaries are already available. So we do plug and play, and because we don't want to just train the algorithm, we are just using some off-the-shelf algorithm like non-local means and also BM3D. These are the algorithms these are the denoisers that already used for replacing the, let's say, soft threshold. And at the last stage, we are just solving the problem with using the inductive bias of units. So what we found, which we haven't shown in this presentation, is that when you just apply that one, you indeed realize that the solution becomes low rank. Okay, so if we just compare the standard plug and play with single value thresholding, you don't have this extra step, but DIP just make the algorithm complete. That I will show you some results that demonstrate that it is actually relevant. And the point is that it may not just produce as good results as the time that you have enough data to reliably train a very much big model and deploy it, but it is providing very much good results. So one of the points that I want to emphasize is that this proposed technique doesn't have the issue of some singularity that happens when you are just using conventional techniques, which means that you need to specifically follow some settings in the, or let's say some patterns in the missing pixels. You don't need to just be worried about that. So it is very much challenging. It's just dealing with the challenging scenarios when the whole spectral band is just missing in that particular pixel. And the point is that because it is kind of iterative, we can just interpret what is happening in practice, and we can just measure it. It's not just end-to-end solution that we are blind on what is going on. And the other thing is that we think that that's better exploit the underlying structure, instead of just having it has low rank. It possibly just go beyond just having low rank, because low rank is approximately low rank is a good model, but like many other linear models, that when they just replace with deep neural network, they just found that still there are possibly better models to represent the data than just the linear models. So we selected two metrics. One of them is just very much, let's say, mean PSNR. The other one is just SSIM and the average over that. So I will just show you when it's compared with some conventional not learning-based techniques. It improves the performance for let's say 4 dB if you are just fully exploiting PNP. And when we are just comparing with DIP, very much similar to self-supervised. So we have one particular scene. We haven't trained the network. We start training based on that, and we try to just guess what are the missing pixels. So again, when we don't have DIP, possibly we are not still it's competitive, but it's not outperforming the state of the art. But when we have DIP replacing a single value thresholding, we receive the best performance in exam. So I'm showing you some of the examples here. We just compared with some already techniques like deep red, which is have been tested for images and some others. And you will see that some of the results, particularly on the first line, you see that some of the outputs are just kind of smoothed out in some of the other algorithms. But it seems that this DIP managed to just, just keep the very much, let's say, local structures. Okay, so we have tested with different patterns and with different data sets, and different, not data set, different images, because we don't need any data set. We only need a single image. And the results were just very much consistent. Okay, so to just kind of summarize, we found this replacing this singular value thresholding with DIP is actually very much relevant to this problem. Going towards self-supervision is just possibly right decision for some applications that the problem size becomes unmanageable, and you cannot just learn reliably a model. And I don't want to emphasize that it is just generate some side-by-side results to fully fully trained models. So as the future directions, we just propose checking the convergence of these algorithms. Whenever you just replace some components with using plug and play, as you just heard in a plenary talk, you need to just make sure that you are not just going, you are not exploding the results, the output. So you need to have a mechanism to just control it. And I just want to say that we just, literally yesterday we just submitted a journal revision that shows the convergence of these algorithms under some mild condition. And we are just so one of the things in DIP is just what is the inductive bias of that network. So how we need to just select that network which performs the best. So still, this is an open question. And I just want to add that in DIP, one of the key factors is that when we stop. So earlier stopping is crucial in DIP. Otherwise, you are just overfitting and you just you do not get the good results that you want. There are some mechanisms that you just come up with some stopping criteria, but still this is something that needs to be developed. So by this, I very much thank you for listening and happy to just take any questions.
Okay, thank you very much, Mehrdad. So we have time for a few questions.
I have a quick question. So it was very interesting. So when you put the DIP inside ADMM, do you run it at every iteration until some point, or do you just do one iteration of DIP within ADMM?
No, it runs at each iteration.
So at each iteration, you fully optimize your
No,
DIP.
the point is that because at the early stage, you don't need to just go a lot of iterations in DIP. We have a criteria that we stop much early in the early iterations because it's pointless to just go fully, optimize. And then we switch to the next iteration. We wait for the next iteration, and that's the way that we handle the problem.
Just to make sure. So basically, you're trying to basically regress to that intermediate variable, the weights of that DIP, and you run it until your stopping criteria is satisfied, and then you continue your ADMM auto iteration.
Absolutely. So we have more aggressive criteria for the early stopping in the early iterations. Yes, true.
Okay. Another question? And online, is there any question? Okay. So I have one. So related to the question of Ulugh, can we go as far as to interpret the number of iterations of DIP as the equivalent of the rank in the low rank plus sparse model that you started from?
Honestly, I cannot just give a number on the number of iterations, but we try to just manage the computation cost. So we try to just limit the total running time of the algorithm to be as far as the let's say, learning algorithms. So I cannot just give a number exactly how many iterations we did, but we just try to just come up with a time that is not much longer than the conventional techniques.
Okay. And a follow-up question. So generally in the low rank plus sparse model, the idea is that you have a clear separation between the two models because this is the underlying model you assume in order to have on one side somehow the background and then some innovation, sparse innovation on top of the backgrounds. Do you have a similar point of view here for the separation between the denoiser and the DIP branch?
It's very good. It's very good question and very good observation. What we have done, we haven't done this, but we try to just see how different is DIP results to the low rank. I mean, we didn't just investigate the correlation between the denoising and DIP, but what we have checked is that this replacement is, does it provide some sort of low rank? And what we observed is that it is enforcing low rank, but not as aggressive as the singular value thresholding. That's what we observed. But I have nothing to just honestly to just answer the question. But that's a very good observation, and I think we need to just do this.
Okay, thank you.